As we now have the unit functionality described in the specification, we can start with the modeling in Simulink. We open the Simulink Start page. Start with the blank model. We save the model as CNV harness because we will build the test harness for the CNV unit here. And we can start the Simulink Library Browser. Now I need an output block for the output signal out temp, which we can find in the Syncs library. We drag the block to the model and drop it. We can move it. When I click on it, I can also change the name. Our name will be outtemp. Now if I hover over the block, you can see these 4 brackets on the corners of the block. You can change the size of the block by using them. And if I go to the import of the block, I can drag and drop the signal. It is red because it's not connected yet. Now I need an input block and I go to the sources library. Drag and drop the block, then rename it to intemp. In the equation, I see that the input will be multiplied by 9/5. I know that I need a gain block for that. So what I can do, instead of using the library browser, I can double-click here on the Simulink editor canvas and just type the name of the anticipated block, gain. In the block list, you can select the correct block and double-click on it. As you see, it is much faster than using the library browser. So I will close it to have more space for the modeling. Now, as we have the gain block, we have to parameterize it. I can double-click on the block mask to define the parameters of the block. But I also can just quickly type directly on the mask of the block. I can use the brackets to enlarge the gain block for better visibility. I can move the block with the mouse, just drag and drop it. I also can use the arrow keys on the keyboard. It is an easy way to connect it to the signal. It's also possible to disconnect the signal and connect it by hand. And same thing is also possible with the output signal. I can connect it to the output port like this. So the equation defines the slope, 9/5, and the offset, 32. I need the add block, type add, press on the enter key, enlarge it a little like this. I need a constant block. I double-click on the canvas, type constant, enter, connect it, define the offset, 32. So this is pretty much the functionality we need. Now we need to add some annotations for the documentation of the unit. CNV is a title. I also can change the annotation settings here, enlarge the font to 20 and make it bold. And I will type the management summary below. I just copy it from my requirement. It looks good. And now I can actually start testing the model, but you should know that it is more convenient to work with subsystems. To create a subsystem, please choose all related objects on the canvas. The context menu appears, and I can create a subsystem like this. It also works if I use the context menu on a right mouse click. You can use this shortcut. The subsystem will be called CNV. We are done with the modeling. This is our model of the temperature converter, and now we need to simulate it. For the simulation of CNV, we can use the ramp block to generate the input signal with initial value of -60, which is the minimum value in centigrades from the unit specification. To display the initial output below the block, I can open the block properties, go to Block Annotations, and select Initial Output. Now we can see the initial output value below the ramp block. To evaluate the calculated output signal in Fahrenheit, I connect it to the scope block like this. And I also want to compare it with the input signal in Celsius. I can double-click on the signals to rename them. I can right-click on the signals to fork them and connect them to the scope block. The scope import will appear automatically. Now I enlarge the block a little so that the signal lines are straight. Now I can run the simulation. Let's look at the results on the scope. This blue line is most likely my input as it is starting at -60. I don't know it for sure, so let us activate the scope legend. The simulation time of 10 seconds is too short. We need to cover at least 160 seconds to reach the specified maximum value. It looks nice. The results are as expected, right?